So today is April 6th, and I tried to do the Lead Code Daily Challenge yesterday actually. I'm still sick, so my voice is horrible. But this one was tricky for me. I wasn't able to do it. So I wanted to make a video just recapping what I learned. Um oh, to start out, so the question is 368, largest divisible subset. And we're given this array. And they want us to return the largest subset in this array where every pair of elements in the subset satisfies this condition where if you have like let's just say answers at I is X and you had answers of J is Y, then if we mod X by Y, we get 0. So think of X as 4 and Y as 2, that would equal 0. If X is 10 and Y is 5, that would be 0, right? You could like try this with a bunch of things and notice that in this case, for X mod Y to equal to 0, we always we could observe that X has to always be greater than Y, right? I hope that makes sense. Like there's no way 4 mod 16 is 0, because I believe 4 mod 16 would just give us 4, right? 4 4 mod 16 just gives 4, yeah. So anything less than doesn't work. So first of all, before getting into anything, I think it would be helpful if we just like sorted the array so that we know exactly what to expect. So I'll just write like sorting up here. And then since so this type of problem, I kind of knew that we had to use dynamic programming, but those dynamic programming problems I feel like are very hard for me, so I still need to work on that more. But we could definitely use dynamic programming for this problem. And what dynamic programming can do is it can actually store the length of the subset that includes some element at I. Right? So like if our nums was 1, 2, 4, and 8, that means our DP would be the exact same size. And it would just say how far of a subset we can get. So like with 1, maybe what 1 can be its own subset. So 1 mod 1 is 0. And then if we did like 2 mod 1, we could get 0 again, right? So this would be like a 2 because we're building the lengths. And then we see like later we could do like 4 mod 2, and then we could like build that length. So it'd be like 3, and then 4, like we could just keep building. So what this means is that at nums of 8, DP, or at nums of 3, DP of 3 will give us 4, meaning the length of this largest possible subset is length 4. So if this question asks us to return the length of the largest divisible subset, then this problem would be done, right? We would just return dp of the max of whatever this array is. But that's not the case. Also, to make it a little bit more interesting, what if we had like 1, 2, 4, um, 10. Actually, that would be the same. Anyway, scratch that. 1, 2, 4. 1, 2, 3, 4 is fine. So not only do okay, what this means is obviously we gotta sort it. We gotta use some sort of DP, right? And then something else that I don't have that much knowledge in is path reconstruction. And do it like creating the DP is one thing, I think is one chunk of the problem. So this is just like a small part is sorting, but I think a big part is obviously DP. But then we also want to reconstruct that large subset. So that's another big part. And what that does is every time we fill in the DP with something better, let's just keep track of where we came from. And this could be in like some sort of previous state, right? So originally, like at DP 0, it's none because we didn't come from anywhere. But then when we go to the second one, and then we see that 2 mod 1 is actually 0, then we could say, oh, the previous was 1. Or then for 3, since we're changing it from 2, we could say the previous was at, oh, sorry, this is indices. So index 0, index 1. And then finally for this one, it would be like, oh, we looked at the one at index 2. So that means our previous is at index 2. So once we could like build something like this, then we could answer the question, right? So a couple things. Let's get the length of nums. Let's sort it. Let's create our DP array, which originally could just be 1. Let's have a previous. That's all nuns times n. And then now we could just like have a pointer like an I and j. And then like if we had I over here, that means we just loop from j all the way to I, checking the mod situation, right? So okay, so for I in range, we could start at 1. Yeah, we start at 1, go to n for j in range of I. So now, since we sorted it, we know nums at I, since it appears later, we know that nums of I is going to be greater than nums of j. And I think we could do like, wait, let me think. If nums of I is mod nums of j is equal to 0. So now we found like a possibly valid answer, but now we just need to compare the DP, right? So if the DP at j plus 1, because we're about to add the nums I into that subset, if that's greater than just dp of I itself, then let's set dp of I to dp of j plus 1, and then we could set our previous to dp, or sorry, previous at I is equal to j. Like if we're filling in let's just say we were trying to fill in the dp of 1, and we were using the value from 0, that means our previous was 0. So our previous at index 1 should point to 0, which is j. Okay, so that's the whole like dp part. The max of this dp is where we should start reconstructing from, right? Because that's our answer. So max dp is the max of our dp for I in range n minus 1. We could work backwards to try to find where the max was. And then once we find our max, like our max was right here, then we could start reconstructing. So if dpi is equal to max dp, then this is where our result will be held. And then we would just return a result. And then it would never go to this. I'll just do a empty array. But this is it. Like, once we find that dpi is equal to the max dp, our res should be should include nums at I, right? So we want to include this one, and then we could have like a current is equal to I, and then we could do while prev at cur. Prev at cur is this one, points to 2, while prev of cur is not none, right? Then we could set our cur to be prev at cur. So now our current would be 2. So here's our current is going to be 2. And then we could do res dot append nums at cur. Nums at 2 is just 3. So now we're adding 3 in there. And then it keeps looping, right? Now previous at 2 is 1 right here. So cur is equal to previous cur, which is 1. And then res append nums at 1, which is 2. So we add 2 in. And then we just keep going all the way, and then we add 1 in. And then that's our path reconstruction to our result 1, 2, 3, 4, which we return here. Cool. Awesome. So time complexity is n squared right here. And then the reconstruction is just linear. Time and space is n squared because we have to have all of these like dynamic programming arrays to help us get to the solution. But yeah, I mean, I didn't come up with this with my own, and I didn't even explain it that well. Just wanted to document my process, my progress. I think this is actually a really good problem because I think DP is pretty tough. Like, it just takes a lot of practice, and I still need to do a lot of that. But I haven't seen a lot of path reconstructions that use DP. I could think of only like one question that I've done in the past that does something similar to this, and that one I failed as well. So definitely need to practice more of this path reconstruction with dynamic programming like combo. But yeah, see you guys tomorrow.